Time for a pop quiz. Easy as pie.
Hello everyone and welcome on in. My name is Penn Center and we're here for presentation number 5 of the Real Analysis Reading Group. Just about to get started here, we're just waiting for ads to roll through on Twitch. That'll be in about 1 minute. Hi Martin, welcome in, how are you doing? Oh McKenna, how are you? Crazy, hi! What's this about? So this is our Real Analysis Reading Group. Today we're going to be talking a little bit about functional limits and continuity. And for those of you in the audience, feel free to use the chat over on the side. I'll be monitoring the chat throughout the presentation as long as it doesn't go too quick. And McKenna's here, so McKenna can also moderate chat a little bit. Doing good, finally woke up. Oh! Classic Saturday moves. It's only 10 o'clock here, not too early. I was at least able to sleep until about 8. What? It was a classic A plus 1, A minus 1. Oh yeah, the 16 times 14. I got you, Martin, I got you. Hi, Pluto. I love analyzing real things, true. I was gonna say, Martin, it's really late for you. 2 a.m. Oh gosh. Yeah, good night. Have a good sleep. Oh god, you could say I'm at my limit. Oh no, the dad jokes have started already. Holy, what's going on with my stream deck? Why is everything so slow? You need to go before you stop functioning. Stop it. Stop. Alright, well let's get geared up and ready to go. Bye, Martin. Have a good day. Oh god, the main thing I'm looking for between lectures is a sense of continuity. That's terrible. Terrible. Terribly good. There we go. We finally got our drum kick for today. Anyway, welcome on in, everyone. My name's Penn Center. McKenna and I have been organizing the Real Analysis Reading Group with a little help from Zyphon in the Mandelbrot Mathematics server. If you would like to get in on the action and be notified of when things are upcoming for the Real Analysis Reading Group, just send me a DM at some point and I'll get you into those channels today. We've already done a fair amount of work, so we've done a lot of work with like proof techniques, how to think about things logically. We looked at sequential limits, including some of the fundamental theorems over there, like the Bolzano-Weierstrass theorem. Last time we got together, a couple weeks back, we looked at the topology of the real number line. That was a nice presentation from Slender. And so what we're going to do now is kind of work our way into thinking about functions and limits of functions and how that backbone works for calculus. So as always, if you have any questions along the way, this is usually just kind of like a one-way kind of lecture, but I'm open to answering questions. If you do have questions, feel free to throw them into the chat. But just for sake of ease of organization for these presentations, we don't usually allow anyone else to take the stage. And today is just going to be like a super chill. We're going to write down some notes so it doesn't go too fast.
Oh, yeah? Prepare to be iterated.
Hey! Suishi there. Thank you very much for the follow. Much appreciated. I needed exactly a distraction while I went to, like, draw my first picture of the day. So that was great timing. Okay, so let's kind of start thinking about, for those of you that have taken calculus, you want to start thinking about, what does a limit mean and how we want to go about tackling that with more of a, I guess, kind of grounded definition. So let's say that we did have, let's say a limit, let's call it capital L, and then what we're going to do is just kind of like bound that limit with like a little neighborhood. So we're going to go ahead and do like an L minus epsilon and an L plus epsilon. Now, with regard to our sequential limits, this epsilon was kind of given to us. We needed the sequential limit stuff to work for all values of epsilon. So kind of think about this as kind of like a call and answer. So we're going to be given a value of epsilon, and we need to construct what we call a value of delta. So this particular band that kind of encompasses our limit L, or at least the limit that we suspect our function to have, it's going to necessarily create bounds down here around the particular C value that we're curious about. So there's going to be a particular value somewhere along the x-axis. We're going to call it C. And we think that, oh, for fuck's sakes, technology. I swear to God. Oh, there it is. What the hell? The power went off in my house last night, and everything got reset. So whenever OBS resets itself, sometimes the Elgato stops working for some reason. Anyway, we'll keep trucking, and hopefully we don't run into too many technical difficulties. But the idea is, we kind of suspect that around this x value of C, we have a y output value of L. At least in the case of a nice continuous function, although we don't particularly care what's happening directly at C. But the thing here is, in green, we need to basically be able to kind of capture all of our x values inside of a neighborhood. So what color should I pick down here? Maybe I'll pick red just so it stands out. So we have to be able to construct a delta so that like all of our stuff is going to fall inside the green bands that we've drawn. So that's how I kind of think about functional limits. Right, so given a particular epsilon, I can kind of draw where I suspect the x values to be contained. That's the green band. And then I need to be able to construct a delta that actually contains, that is contained within those green bands. So that's kind of the idea here. So our goal here is to interpret when we say in calculus the limit as x approaches c of f of x is equal to L, what does that actually mean? And so typically in our calculus class, we might say something like f of x. So this is very classic Stewart calculus kind of approach. To say that f of x gets arbitrarily close to the limit L as our x values get arbitrarily close to c. Pluto says there's an XY graph for my pee-pee frogs. Yeah, there you go. So this is kind of like a typical way that we might try to introduce this in a calculus class, but let's kind of get down to some of the structure of what this actually represents and what this means. So formally, we have something along this lines. We'll say that we have a function. We'll just call that function f. And let's take c to be a limit point of our domain. Sometimes I believe this is called an accumulation point as well, but like in the topological sense, we're basically saying that any intersection kind of around this limit point is going to contain a non-empty part of A, basically. And so here it is, friends. We say that the limit as x approaches c of f of x is equal to capital L, provided that for any epsilon bigger than 0, so you give me a particular value of epsilon that's positive, I'm going to say there exists a delta. That delta also has to be a positive value. And then I need to show that the implication is true. So I need to show that provided the distance from x to c always remains less than delta, this should imply that the distance from the functional values, right, the output values, to L are always bounded by epsilon. Now, just take a quick notice here. I have put a lower bound of 0 here. Because a limit point doesn't necessarily have to be contained in A, there's a little bit of kind of subtleties happening here. So basically I'm saying like x, we don't really care. I don't really care about what's happening directly at C. So that's usually why the textbook has used this kind of greater than 0 lower bound, right? We don't want it to equal 0. We don't need x to be identically equal to c because this limit point doesn't necessarily have to be inside the domain. Hi, Ben. Welcome in. When did you start doing analysis? This is our 5th class, man. We've been doing analysis for a while. Angie, I notice your hand up to speak. Feel free to write anything you need in the chat. So this particular definition can be a little bit tricky, I think, for students that are kind of new to analysis and new to kind of this approach to bounding things. But there's a couple pieces here that I think are important for us to kind of deconstruct before we start doing some examples. The first is that if I want to prove something using this definition, we start with a universal quantifier in the forwards direction. A universal quantifier in the forwards direction usually means we use the choose method, so we just kind of pick one of these objects and roll with it. So we have a universal quantifier in the forwards direction. That means we're just going to choose an epsilon with the particular property that we want. In this particular case, we'll just choose epsilon bigger than 0, and then we'll be on our merry way. Now, the next thing that we have in the forwards direction is an existential quantifier, so there exists a positive delta. So this existential quantifier in the forwards direction usually implies that we have to construct a delta. And I would say that, like, in a lot of the cases in the textbook, this delta is probably going to depend on epsilon. Not always, but probably. So that should feel very similar to how we were working with our sequential limits. For the sequential limits, it was, what was it? It was like for all of the n's bigger than some capital N, something happens. So it's kind of the same thing. We were constructing the capital N in terms of epsilon. Same thing here. We're going to be constructing the delta in terms of the given epsilon, because we know that epsilon exists. And I guess the last thing we need to look at is this implication. So there's kind of two ways to think about this. I tend to approach this situation from a very constructive perspective. So the idea is usually I'll start with the conclusion and I'll try to construct my delta using the conclusion. And I don't even need to really set that less than epsilon, but what I need to do is kind of start with this absolute value typically and kind of manipulate it to try to get the x minus c. So this is what we call the construction phase. I'm kind of constructing and trying to figure out what delta looks like. Once I know what delta is, then I have to actually come back and provide the proof. And for those of you that are curious, I will actually print these off in PDF format. I'll upload them for you after if you want to kind of come back and go through these again, or use these for future notes for a future course. So I think right now we'll jump into an example so you can kind of see like the idea of how I would think about going through one of these proofs. And they can be quite involved. We'll do a couple more simpler examples so you can get a sense of how the construction and how that proof works. And then I would just say, like, just go try a couple of things and post some of your attempts in the discussion forum if you want in the real analysis course, and we can take a look, you know, and see what are hard things to prove, what are the strategies that we have, and things like that. Thank you for the notes. Yeah, no worries. So Maxi's asking, does in the forwards direction mean the left side of an implication? Okay, so Maxi, what I'm thinking about is if I want to prove something using the definition, the very first thing I'm going to encounter is the for all statement. The next thing I'm going to encounter is the there exists statement. And then the last thing I'm going to encounter is the implication. So I need to deal with the for all statement first, which means we just have to choose an object with the property that we have, so the choose method. Then I hit the there exists statement. I have to deal with that next, which means I need to construct a delta. And then the last thing I need to do is provide the reasoning for the implication. So we assume the left-hand side and then try to show that the right-hand side is true. But yeah, I guess like I'm reading this in a forwards direction saying, oops, I've hit a UQ, then I've hit an EQ, now I have to prove the implication. Hopefully that makes sense. Hey, Matt Spellbook. Welcome on in. How are you doing, my friend? Give a quick little shout out to our good friend, Matt Spellbook. Let's see if I can actually type things. please join us in following Math Spellbook. They are a fairly consistent mathematics streamer and have recently been doing, some multivariable calculus, some differential equations, and hopefully real analysis soon. What are ML proofs for complex analysis? What's that? So we'll start off nice and easy with a nice linear function. If we've taken calculus, we know that we can, this is a nice continuous function, so I can just substitute 2 in. There are no holes, there are no jumps or gaps, and we'll define continuity a little bit more carefully in a bit. But this is a nice continuous linear function, so if I put 2 in, I know exactly what I expect the output of this function to be. I expect it to be 7. However, let's try to prove it using the definition. So let's try to see what this looks like, so that when we go to look at a more challenging example, hopefully the process makes a little bit more sense. So I break it up into the construction phase and then the proof phase. So let's take a look at the construction phase first. What do we have to do? We have to start with the absolute value of my function minus the limit, and see if I can try to get x minus c. In our case, x minus c is x minus 2. Megalomorph makes a very good point in chat. It is messy. It's a little bit painful when you start to learn it, and it really is a lot scary when you start to learn it. But as you start to get better and better with the tools and the techniques, it becomes a really, really fun branch of mathematics. And for me, I would say I'm a little bit more weak at my real analysis skills and maybe a little bit better at my complex analysis skills. But it's only because it's been a while. Okay, let's take a look at the construction phase. So our function, f of x, is 3x plus 1. And our x minus c is really x minus 2. And our overall limit, capital L, should be 7. So what we want to do is we want to start at f of x minus L. So let's start at 3x plus 1 minus 7.
Zeta, right? Complex analysis has its charm, but it's often more intuitive. Real analysis, just a zeta headache with all those limits. Choose your equations wisely.
Matt Spell says my math studying is all over the place. I can't focus on, just like eating Lay's potato chips. You can't eat just one. Once you start going, you can't stop. Or maybe it's like Pringles, once you pop, the fun don't stop. Is complex analysis just as difficult as real analysis? I would almost venture to say that real analysis might be slightly more challenging, to be honest. There's a lot of things that happen, at least in the introductory parts of complex analysis, that make it just a little bit more enjoyable compared to real analysis. And that's totally a personal opinion. So what I'm noticing as I start to look at this f of x minus L is that I get 3x take away 6. I can factor out that 3 from the absolute values, and that's going to give me x minus 2, and that's exactly what I want. Right? That's exactly x minus c. Now, if all of this was less than epsilon, then theoretically, I could probably say something like x minus 2 should be less than epsilon over 3. And now I know what my delta looks like. So if I pick a delta value that looks like epsilon over 3, I should be able to work backwards to get the implication that I want. So that's the construction phase. Start with your f of x minus L, try to manipulate it around and find your x minus c, and then we're going to try to make an educated guess on what we think delta looks like once we find that x minus c. Now, it's not always so easy, as we'll see in the next example, but let's take a look at what the proof might look like. So I've done my rough work, and now I want to show my instructor that I know what the hell's going on. So the first thing I need to do is deal with the universal quantifier. So I'm just going to let epsilon be bigger than 0. Cool, I've dealt with the epsilon part. Next thing is there exists a delta bigger than 0. I've already gone through the construction phase. I know how I want to pick delta. So I'm just going to tell the reader I know exactly how to pick delta. Let's take delta to be equal to epsilon over 3. I've constructed it. I know exactly what it should look like based on my previous work. And so the last thing we need to do is deal with this implication. So we're going to assume that the left-hand side, or the hypothesis, is true, and we're going to try to show that that leads to the right-hand side. And I already kind of know how this is going to work, but let's just write it down. So let's consider, well, actually not even consider, let's assume that this x minus 2 can be bounded between 0 and delta. There's some cool comments. I'll circle back to the comments in a bit. Just kind of for sake of ease here, I'm going to drop the left-hand side. Okay, and I'm going to kind of, in the back of my mind, know that I can't pick x is equal to 2, for example. Okay, so we have the following. If I input delta, I get that this is now bounded by epsilon over 3. I can multiply both sides of the equation by 3. Or both sides of the inequality, I should say, by 3. And then we can distribute that 3 back through the absolute values. Now, the last thing I need to do is I need to get the f of x minus L back in here. And how did we do that before? Well, 3x minus 6 is really the same thing as 3x plus 1 take away 7. Right? I know how to do this. I already went through this process, right? So I know that I can take this minus 6 and I can break it up in the following way. And now I have that f of x minus its limit can always be bounded by the given epsilon value, right? Provided that I take delta is epsilon over 3. So there you go. That would be proof of the first one. So I'll let that sink in for a moment, and if you have any questions, you can let me know. Megalomorph says, complex analysis is nicer because it's so much more rigid, and you have much more algebraic seeming arguments using Laurent series. Yes. And you have residues, which is a big part of the initial part of complex analysis, yeah. And they're very magical, I agree. And I guess that's true. Megalomorph is saying the functions that we typically use in complex analysis, which are conformal maps typically, right, happen to be nicer, and they have a very narrow application. Yeah, so there's something about the geometry. The geometry of complex analysis is really cool. It's really nice. Not conformal maps, sorry, analytic. Well, can I use those interchangeably, Megalomorph? Conformal is angle preserving. Are analytic maps the same thing? There's so many definitions that over there. But it's usually analytic maps. Like, I'm trying to think, are analytic maps? I think analytic maps are conformal, right? They're at least locally conformal.
Time's precious. Let's calculate your boredom away. What do you need? A Zeta awesome idea or a mind-bending theorem?
Gotcha. So analytic maps are conformal, but conformal maps are not necessarily analytic. Epsilon looks like tiny sigma. Hi, better yet. Welcome in. Congratulations on your VIP. Unable to add VIP, what? Oh, it's because I spelled it wrong. I almost VIP'd the wrong individual. That would have been funny. Math spell is, so solving for delta is usually the scratch work. Yeah, exactly. Trying to figure out how to write delta down is always the rough work. Okay, so that was kind of a warm-up example. These linear ones tend to be very, very nice, and you always usually get epsilon over m as your delta value. So let's crank this up a notch. Let's try to prove that the limit as x approaches 2 of x squared is equal to 4. Access to the nuts command again, true. Yeah, McKenna's right. Epsilon-delta proofs can get pretty awful pretty quickly. It depends on the function you're working with too, right? Yeah, analytic means given by a power series. Holomorphic means having a complex derivative. Those happen to be equivalent. Conformal is angle preserving, right? And holomorphic maps are conformal except where the derivative is 0. Yeah, okay, that's what I was trying to remember. Yeah. Yeah, and it's because of that that really interesting geometric local behavior. Yeah, where multiplication, where you get a multiplication in a stretch, right? Okay, well, let's take a look at this. If I want to do some construction, I need to take my f of x minus L and see what's going on. So our function in this case is x squared. Our limit is 4. And this is a difference of squares, so theoretically we should be able to break this up into like an x minus 2 and an x plus 2. And that's helpful because now I can see that this is the x minus c part that I'm looking for. But that does leave us with a little bit of an oddball over here. What do I do with this? Because kind of my thought is, I know that all of this should be, or I want this to be less than epsilon. So kind of the idea is I want to be able to take this x minus 2 and kind of divide by this x plus 2. Like I kind of want to do something like this. But I can't really have x over here because x varies. So it might be nice to kind of figure out how big this x plus 2 could get in the neighborhood that I'm working in. If I could figure out how big x plus 2 gets in the neighborhood that I'm working in, then I can just replace this with a number, and then I can divide epsilon by that number. So the question is, how big does our x plus 2 get? So I guess if you're kind of going back and thinking about our original picture, if we take a parabola and we start kind of thinking about these epsilon bands as kind of getting bigger or closer, you might be able to see that like as epsilon gets bigger, because we're working with a parabola that's kind of got this parabolic arc, as epsilon gets bigger, the x plus 2 is probably going to get bigger, and as epsilon gets smaller, the x plus 2 absolute will probably get a little bit smaller. So what we kind of classically do here is we try to kind of pick a nice value for epsilon. So what you'll see the textbook do is they'll say, well, what if epsilon was 1? Usually we don't really care about large values of epsilon. We usually only care about kind of small positive values of epsilon. So they're going to say something like, I don't know, let's just let... Not like let, I guess it's just like consider what happens, right? So what happens if epsilon is 1? Is this right? No, I think it's delta that we want to fix here, right? It's because we're along the x-axis. So we're along the x-axis, my apologies. So we're trying to kind of figure out what's happening around x is equal to 2, and we're trying to bound an x plus 2. So let's just take a particular delta value and see what happens. So what if x minus 2 was bounded above by 1? And like I said, we kind of expect these delta values to be a little bit smaller, so kind of taking an upper bound of 1 isn't going to make or break us, and I'll show you kind of why that works with the proof. So if this was the case, would it be possible for us to get an x plus 2? And so I always kind of think like this. If the difference between x and 2 is always kind of bounded between 0 and 1, then, maybe the worst lower bound that I could get for this would be minus 1. Now, usually we want this to be positive, but just for maybe the sake of kind of the construction argument, I'm just going to do this. So I'm going to say, well, if the absolute value of x minus 2 is always bounded above by 1, then x minus 2 itself should always be in between negative 1 and positive 1. But I want to know information about x plus 2, so I need to convert this to an x plus 2. Now, I would have to add 4 to be able to do that, right? So I'm kind of adding 4 to everything and kind of seeing what pops out. So 4 and 1 would be 5, and 4 take away 1. Not that I am particularly fussed in this case about the lower bound, but my lower bound would look like 3. But what I really care about is that this is always kind of bounded above by 5. So I could say that this x plus 2 is always bounded above by 5. Right, so that's what happens if delta is exactly 1. Trying to go through Abbott while going through these lectures. And Abbott doesn't do a great job of like showing you the construction and the proofs. That's all. So that should be enough. If I know the upper bound of x plus 2 is 5, I can just put 5 here, and I could say that delta should be chosen to be epsilon over 5. Right? So now we have a relationship that looks like this. We know that this needs to be less than epsilon, but if this is 5, then I know how to pick my delta. My delta should be epsilon over 5. So let's come back and just see how that proof works. And maybe I'll just do it down here. All right, deal with the universal quantifier. Deal with the existential quantifier. Oh, I apologize. This is a bit of a tricky case, isn't it? Because we are actually going to have to make a choice here. So let's talk about this a little bit once I get set up. So we made a choice up here, right? We made a choice to choose delta equals 1 and see how that helped us bound one of the terms inside of the expression that we were working with. When we did that, we ended up getting a value for delta. And so whenever we kind of force a choice in order to bound something, we usually now have to introduce this new structure where we take like the minimum value for delta. And so there's kind of like this little game. I mean, if delta, if we know delta is equal to epsilon over 5, how do I want to say this? I want to make sure that I say this correctly. I think Megalomorph actually put it very well in Twitch chat, saying that kind of the idea here is if it works for a specific value of delta, any smaller value of delta should also be okay. So by taking the minimum choice between these two things, like that's what I want, right? Like we chose a very particular case of delta equals 1. But any smaller value of that should be fine. So that's kind of the idea with this idea of like taking the min. But I want to show you kind of the two cases that pop out. So there's case 1. Just so you can kind of see that my arguments are okay. Case 1 is, you know, maybe the min is 1. Maybe that's the minimum value. So this might happen, for example, when epsilon is 5, or 6, or 7, right? So for very large values of epsilon, the min could theoretically be 1. So what would happen in this case? Well, I know that delta is equal to 1, so I know that this x minus 2 is bounded above by 1. And this gives me some information about how big epsilon over 5 is. If the min of these two things is 1, this just means that 1 is less than epsilon over 5, right? And if that's the case, then I should be able to introduce that here as well.
I'm Mr. Meeseeks! Look at me!
Hi, Sensation. Welcome in. So I really have something like this. I can just now multiply both sides by 5. And I'm most of the way there. I just have to kind of convince my readers now that this 5 is is an upper bound, effectively, for this x plus 2. And maybe I can do that work over here on the side. We already know what this looks like. We know that x minus 2 is bounded above by 1. So we know that x minus 2 is bounded between -1 and +1. So our x plus 2 should be bounded by, what was it, 5 and 3, I think we said, right? So if the upper bound for this absolute value is 5, I know that I can kind of introduce something that looks like this. So I can introduce this extra term that I need in order to get the job done. Like this, right? So I know that this is always less than that thing I was looking at, which is always less than epsilon. Now I can cut out the middleman, and I have that x squared minus 4 is less than epsilon, and that's exactly what we want. So that's what happens if the minimum value is 1. That happens when epsilon is really, really big. But what happens if epsilon is really, really small? Right, that would be case 2. So what happens if the min between 1 and epsilon over 5 is actually epsilon over 5? So in this case, we're really looking at x minus 2 less than epsilon over 5. We begin here already. But the cool thing is that now this is going to imply that epsilon over 5 is less than 1, right? Or at least, I guess there could be theoretically could be an equal sign here too. But maybe just for the sake of making the argument solid, we'll throw an equal sign here. And so now we kind of have this series of inequalities in place. So that means that x minus 2 is already less than 1 as an upper bound. It's kind of like magic, right? And so we already know that implies that x plus 2 has to be less than 5. We've already seen that argument already. And then we can just get on with our lives. We can say, okay, well, this is really just 5. X minus 2 is less than epsilon. And we know that this is going to turn into an x plus 2, x minus 2. Because we can introduce that because 5 is the upper bound of that absolute x plus 2. And then we kind of get to where we need to go. So again, I'll kind of zoom out so you can kind of see the overall idea of the proof. But when we go to prove these kinds of things, because of this kind of inequality relationship with the min, you usually only ever see textbooks prove it once, right? They only ever prove one case, and usually it's the case where like epsilon over 5 is less than 1. So you can kind of see how similar these cases end up being. So we don't really write them both down because of that kind of nice relationship between the two particular cases. Yeah, it's really, really interesting. This stream needs more Wind Waker. I haven't played Wind Waker in a long time. So there you go. There's a couple examples of functional limits, how to think about them using the definition. So let's move into what I would consider to be like a really interesting topic here, which is what we call the sequential criterion. For functional limits. So there's a nice theorem in the textbook. It goes something like this. It says, given a function, and we're just taking some domain of R and a limit point from that domain. Oops, it's actually not in A. Then the sequential criterion says that the following are going to be equivalent statements. The first statement is that the limit as x approaches c of our function is equal to L. So this is the typical kind of standard way to write the definition that we just talked about in the last section. And they're saying that this should be equivalent to the following statement. For all sequences, and we're just writing our sequences here with the rounded bracket. So for all sequences contained in A, and we're denoting the sequence as x sub n. And we need those sequences to satisfy two things. We need them not to be identically equal to C, and we need them to converge to that limit point C. Provided those two things happen, then as I go to input those sequential numbers into the function and kind of find the outputs, the sequence of output values should converge to the limit, to capital L. Yeah, thanks, Matt Spellbook. Have a good rest of the day, man. So it seems kind of reasonable that this should be true, although real analysis can get a little bit weird. But like, what's this saying? It's saying, you know, if I have a C down here and, you know, C might not be a part of the domain, But what we have is we have kind of limits that are tending towards C, right? So I have kind of this sequential limit. Like, I don't exactly know what it looks like. Maybe it looks something like this, but it's kind of tending towards C. And then I have this limit value, capital L, again in the real number, so I'm just kind of picturing that along the y-axis. Now, all of these can be viewed as inputs for the function that we're working with, and all of these end up popping off somewhere along the y-axis. So I don't exactly know where they end up, but maybe it's bouncing back and forth. I don't really know what's happening. But the idea is as we kind of convert through f, the sequence that I get on the y-axis has to converge towards L. So like this feels kind of like a reasonable thing to say. This sequential limit as I move it through f, this sequential limit that converges to C as I move it through f should also end up being a sequential limit that converges towards L. It seems like a thing that is realistic. It feels, well, actually maybe I'll leave that in case you want to see my beautiful hand-drawn ideas for later. So it seems reasonable. Let's see what the proof looks like. Now, this was probably the hardest part of the notes, so bear with me here as I try to remember how this proof goes. This was not an easy proof to do. So we want to first do 1 implies 2. So I want to, if I'm doing it in the forwards direction, we're going to assume that statement 1 is true, and we want to prove that statement 2 is true. So let's assume that the limit as x approaches C of f of x is equal to L. And our goal is to show that all sequences satisfying these two properties, we have that the f of xn converges towards L as well. So if we know that the limit as x approaches C of a function is L, this means that if I'm given some positive epsilon, we know that there exists some positive delta, satisfying that implication in the definition. So that implication in the definition looks something like this. Okay, so we do have that, right? If we're given an epsilon, we know we can construct a delta that makes this implication truthful. So now let's kind of consider what's happening in this second part. So we're going to now, maybe grab, right? This is a universal quantifier. So when I'm going to kind of think about proving statement 2, I can actually grab a sequence that satisfies the two properties that I want, and my goal is to show that f of x sub n converges to L. So I'm just going to pick, one of these xn sequences such that xn is not C and xn converges to C, and let's kind of see what happens as I push it through the function. So let's grab, right, so we call this the choose method. Let's just grab one of these sequences. Let's make sure it satisfies the properties that we need it to. And then I'm going to use the fact that this x sub n is a sequence, and we know that this sequence converges to C, so I should be able to get some information about this convergence. So since this sequence converges to C, we know that there's some capital N. Okay, so there's some capital N inside of the natural numbers. Such that whenever our index little n is bigger than or equal to this capital N, this is going to imply that our x sub n minus this limit point should be bounded above by delta, right? So we know that this, basically we know that this particular delta exists. And I guess for sake of argument, is this going to be the same delta? Well, let me look at my proof. But I know that this particular delta exists. So if we want to kind of like emphatically show the reader that this delta exists, we could call it like delta prime, or we could call it delta sub-zero or something like that. But it's important to know that this particular delta exists. And so once we know that we have this particular delta, now we can go back to this idea of the limit, right? So we know that this implication is true, right? So if I can kind of bound this x minus c by delta, that should imply that my function minus the limit is bounded by epsilon. So now that we have this particular argument that our xn minus c is bounded above by this delta, I should now be able to use the implication in star. Let me think about that for a hot second. I might have written that down a little bit incorrectly, but using star, we know that this xn minus c less than delta should imply that all of this is less than epsilon, and that's what we want. Now let me zoom out and make sure that I'm happy with that. And those of you that know analysis maybe a little bit better than myself can correct me if I'm wrong. It's not necessarily that delta exists, I guess, right? Well, maybe. I guess it's more so the fact that you can construct this delta using the capital N, right? So the idea with the sequential limit is for all deltas bigger than 0, there's this n, right? So I think I use delta here to show that, like, once I have this bound for my xn minus c's, I can kind of go back and I can use the implication above, right? This x minus c less than delta in the definition of the limit should work for any value of x. This star implication works for any value of x. In particular, it's going to work for the x sub n's. Right, so I guess what we're doing here is we're just kind of choosing this capital N in such a way to get the implication that we want, and to get the inequality that we want to be able to use this implication. That's really the key idea here, and I definitely struggled a little bit trying to understand what they were trying to do in the book, but hopefully that makes sense. Right, the idea is if it works for all x, it should work for the select x's inside the particular sequence that we're looking at. Now, this is the tricky part of the proof. The 2 implies 1. So the second thing that we have to prove is that, if we have this relationship for all sequences x sub n, this is going to imply that the definition of the limit is true as well. This one's going to take a little bit of work because we do have to negate and contrapose a couple of things. So let's see if I can get the order of things correct here. So let's go by way of contradiction. So let's assume that number 2 is true. Every sequence inside of our domain satisfying these two properties, we know that the fxn's should converge to capital L. So let's assume that that's true, and let's assume that the limit as x approaches c of f of x is not equal to L. So this might need a little bit of explanation. But if I'm looking at an implication, if I'm looking at a P implies Q, and I want to negate that, so to negate an implication, we take P and not Q. So that's all we're trying to do here. So what I'm doing is I'm saying, okay, I have this implication that I want to prove. What I'm going to do is I'm going to negate that implication. And I'm going to see if this, I'm going to like kind of analyze to see, is this true or false? So this is the logic that the book takes. It's going to like look at the negated statement. It's going to show that the negated statement is false. And then they're going to use that to conclude that the original statement has to be true. Vin is saying, I think using lim-sup and lim-imp can give a more unified proof. Oh, I see. Yeah, exactly. We can't use this particular proof for something that goes to infinity. That's absolutely correct. Does this text even go through lim-sup and lim-imp? I don't even remember seeing that terminology in the textbook, to be honest. Shimmering Vineyard. Oh, you're one of those people.
Stupid fractal!
Okay, so I'm happy with that setup. So let's take a look at this. Like, what does this mean? And Vin, if you have an idea of what that proof might look like, it might be beneficial to put that proof using the lim-sup and lim-imp into the regular chat. People might be interested in seeing what that looks like. But I'm not sure I trust my skills enough to be able to pivot to look at that kind of proof right now.
Why did you even rope me into this? Cause he roped me into this. Well, him over there, he roped me into this. Well, he roped me into this.
So the reason why it might be interesting to see Vin's argument is maybe we can skip having to deal with all of the like weird negation that's happening, which I think was the hardest part of thinking about the proof. Because like it's easy to negate this statement because we just put a not equal sign here. But what does this really mean in terms of the definition? Well, it really means that, given some epsilon, so there exists some positive epsilon, such that for every single delta that I can pick, I have that there's like an x in the domain that satisfies these two things, right? So if I try to bound x, if I try to kind of bound the distance from x to c by delta, then it's kind of true that this f of x, the bound of the f of x minus L, this should be not less than, this should be greater than or equal to. That kind of these output values for x kind of land outside of the epsilon band. And that should be true for some particular x in the domain. And so as a picture, we have something like this. Okay, so there's some particular x that kind of lands outside the epsilon ball or the epsilon band around this capital L, right? That's kind of the idea. Okay, let me jot down something here, and then we'll just kind of decompress this and see what we got. So let's take a particular delta, which is 1 over n, and then that way for each n inside of the set of natural numbers, we get the following. We get that this xn minus c can be bounded above by 1 over n. So we're kind of fixing a particular delta. And I made a little note here that this is the given epsilon. Now, let's see. Yeah, so we can do this, right? So we take... we're basically trying to construct one of these x sub n's, I think, right? And I think we're hoping to hit a contradiction, right? That this, we're basically going to try to show that this can't happen, I think, right? And maybe someone a little bit more well-versed in the topological argument can help me out here. I don't think I gave myself enough notes. Okay, I wrote down that the result of doing this, and like I said, this is the part of the lesson today that I was really, really struggling with. Okay, so the result of doing this is a particular sequence, right, that we know is going to converge to C. We know that it's not identically equal to C. And then I write that the fxn does not converge to capital L. Okay, what are we trying to do here? Oh, that's okay then, no worries. Or even if you have like a link too, right? Like a link to be able to see it might be helpful too. If there's a nice resource on like Stack Exchange or something like that. Oh, this is an assumption, isn't it? Yeah, I see. So... Yeah, this is a bit weird to see. I get it. I get it now. So this is a part of the assumption, right? So we've assumed this. Every sequence satisfying this and this, it follows that this. Right, I see. Okay. This is hard to explain. Let's see if I can capture it. So we're assuming this. Right, that I can, anytime that I do this, I also have this particular property, right? That the f of x minus L is bigger than or equal to epsilon. So by constructing this particular sequence, is that right there? Because we're trying to contradict this, is what they're trying to do, by using this. So let me just... I think this is... Does this have to be a bigger than or equals to? I'll have to look into this one. Let me write a little note to myself. I don't know if this has to be a bigger than or equals to, if I wrote that down wrong. But I remember that the idea was, and this took me a little while to figure out, was you have to kind of make this double assumption, but this double assumption leads to the contradiction that f of xn does not converge to L. So we're kind of contradicting the assumption that 2 is correct. So let me get back to you on that one. Is a sequence law that does not converge to L, and the contradiction is that this contradicts the assumption that 2 is true. As a result of that, that's going to imply that our original implication is true. So if someone has some insight there, feel free to pass it along. If not, I'll post it up in the discussion and see if I can get someone to just kind of clarify how that works. But yeah, this was the tricky part of the sequential criterion, was proving that 2 implies 1. And because it had to be, well, from the arguments that I saw and was looking at, it had to be done in this kind of contradiction way. Or at least that seemed to be the way that most people tried to prove it. And it was it wasn't clear. Most of the arguments weren't overtly clear to me, so I'm trying to add in a little bit of context for those of you studying. Let's see. There is so much to do. I haven't even thought about doing anything with regards to continuity yet. But let's take a look at a quick corollary of the sequential criterion. And then I want to maybe take a little bit of a break here. So let's say that we have a function. And let's take C again to be our limit point for the domain. And let's say we have 2 sequences. We're going to call them xn and yn. And those are going to be 2 sequences inside the domain A. So we'll take these 2 sequences in A. We need to make sure that xn is not identically C, yn is not identically C, and that their limits are the same. Okay, so let's make sure they both converge to C. Now, if all of that's true, but we happen to know that the limit of fxn is not equal to the limit of Fyn. Then this is enough to let us conclude that the overall sequential limit doesn't exist. And I write this as a corollary because it's supposed to be relatively clear that this is the case by looking at the sequential criterion. So let's just kind of scroll back. This says the limit exists. All sequences satisfying this property converge to capital L, right? Fx sub n converges to capital L. So kind of the negation of this, right, would be to say, okay, if I can find a couple sequences, right, if I can show that not all sequences have this property, then I know that the limit does not exist. So that's kind of the reason why this is just given as a corollary. And sometimes this is called the divergence criterion for, using sequential limits. So I want to give you an example of how we might be able to utilize this to show that a limit does not exist, and then we will take a little break here. So let's consider a function g and let's suppose that g is given in a very weird way. It's 1 if I know that x is a rational number, and I know it's 0 if x is not rational. I wonder if Desmos can plot something like this. It probably can't. But the idea is you get, like, what does this look like? This is a weird looking thing. Because we know that, like, the rationals... What is it that... Like, is it that the rationals are dense in R, right? And the irrationals are dense in R. I'm pretty sure that's a valid statement to say. So you end up getting, like, this weird, like... Maybe I'll do it in a couple... You get, like, kind of like a bunch of stuff happening, like, at 1. And you get, like, a bunch of stuff happening at 0. So this is a weird-looking function. It's really, really weird. So let's consider something at 1. Let's consider x is equal to 1. And we might ask ourselves, does this function have a limit when x is equal to 1? Well, using our previous corollary, what we could do is we could create two sequences, right, that are not identically equal to 1, and have the same limit, right? But we want to show that the limits of the outputs of these two sequences is different. So let's construct our first sequence using only rational numbers. So let's do 1 plus 1 over n. Hopefully it's clear here that as n gets really, really big, this should converge towards the value of 1. So this is the kind of the purple value that I have over here on the right-hand side. Right, all of these xn's should be rational numbers because we're just adding a small positive rational number to this, and we know the rationals are closed under addition. So our function evaluated at each of these points should tend towards 1. Right? Any of these numbers inputted into g of x should give me an output of 1. So g x sub n should converge towards the number 1. Hey, Turdy. How are you? So that's the first sequence. Now, as you might guess, the next thing we want to do is try to capture kind of what's happening down here for g values that are coming out to be 0. So let's pick a second sequence.
Well, that one over there wrote me into this. Well, he wrote me into this.
And let's just maybe ensure that for all positive integer values, we get a irrational number. Right, so let's do something like 1 plus root 2 over n. Now, I can certainly argue here that because n is in the denominator and n is getting very big, that this root 2 over n should eventually tend towards 0, so that y sub n should converge to 1 as n gets really big. However, each y sub n is not a rational number. So this would imply that g y sub n, all of these are zeros, right? All of my output values here are 0, so that particular sequence is just a full sequence of zeros. So that g y sub n should converge towards 0. And this is now our problem. Our problem is we have these two outputs that converge to different things. So maybe I'll just say the limit of this particular sequence is not equal to the limit of this particular sequence. Oh my gosh, writing is hard today. So we could say that the limit as x approaches 1 of g of x does not exist. We love real analysis, hellish functions. True. Yeah, this is one of those weird there's a lot of weird functions inside of Abbott, to be honest. What is this sorcery? Yeah, this is sorcery. And speaking of sorcery, Jebel's theme in the background, yeah, totally works. Okay, so there you go. There's an example of how we can... We now have at least a way to kind of deal with these weird functions that we suspect the limit may not exist. I just have to find two sequences along the x-axis that tend towards the same limit and show that the output sequences tend to different values. And that's enough to guarantee that the overall limit for this function does not exist. Cool. So this, I think, is a good time to take a little break. I'm going to grab just a little hydration break. And then we're going to move into, I want to talk a little bit about the algebraic properties. And maybe give some insights into how to prove some of the algebraic properties when we get back. And then if we have some time, we'll take a look at some examples as well. Also, by the way, in some sense, I wrote this down as a remark, but in some sense, what this corollary is giving us is path independence, right? So it doesn't matter how we approach C along the x-axis, the output sequence should always tend towards L, right? So it should be path independent is basically one way of saying this. So that's a very common thing to hear in a calculus class as well. Okay, so I'm going to take a little bit of a break, my friends, and we'll be back in like 5 to 10 minutes.
Time for a pop quiz. Huh. Nicely integrated.
All right, friends, welcome back. Next up on the block today is talking a little bit about the algebraic properties of functional limits. And I see Vin typing. I'll just read the theorem off. We'll see what Vin has to say here. I wanted to give a little bit of, I guess, kind of backbone structure on how some of these proofs are done, since they can be a little bit complicated. And I think it's worthwhile to see some of the basic ones and get a general sense of what's happening in the background here. So we usually cover these in a typical calculus class. We have two functions, f and g. We might say, you know, that the limit as x approaches c of f is L, and the limit as x approaches c of g is m. And then we usually have some of these algebraic properties, like multiplication by a real number k. So let's say this k is a real number. It really is just like k times the limit of f of x.
Prepare to be iterated.
Pre-cut moth, thank you very much for the follow. Much appreciated. For number 2, right, the addition of these two functions should lead me to L plus m as my limit. The multiplication should lead to L times m, and the quotient should lead to L divided by m, provided that m is not 0. So this is what the theorem states, and what I'd like to do is just kind of go through the logic of how to prove these things, just so you can kind of get a general sense of what that argument looks like, because these kinds of arguments come up a lot in analysis where we're trying to prove sums or multiplications or divisions, and they're all kind of tackled in a very, very similar kind of way. Now these are limit proofs, so we normally would kind of go through the construction phase and then the proof phase. For the first one, I'm just going to go ahead and prove it. For the second, third, and fourth ones, I want to show you the construction phase, like what's going on in the background that causes a need for something else to happen. For the first one, you can go through the construction phase if you want. It's fairly straightforward. But we're basically just going to say let epsilon be bigger than 0. Actually, I guess there's two cases I have to be a little bit careful of here. So case 1 is that k is equal to 0. Because I'm going to be choosing my delta in a very particular way, and k equals 0 is not going to work. So when k is equal to 0, we just have that this multiplication really just becomes zeros. We just get the limit as x approaches c of a bunch of zeros. And really, no matter what no matter what the limit is for f, this should work, right? Because we just get a full sequence of zeros here, and then that's really just 0 times whatever the limit is for f of x. Oh my goodness, we are getting rated. Hello, Zach E to the 2i pi. How are you doing? How was stream today, my friend? Any cool questions you were working on today?
Oh yeah? Prepare to be iterated.
Entropic Universe, thank you very much for the follow. Hi Jeff, welcome in. It's going to be chaos here for a hot second, for those of you on Discord. Did some Pascal's triangle, that's really cool. Pascal's triangle mod P, that sounds crazy. So what are we up to right now for those of you raiding on in? My name's Penn Center. Zach and I do host our linear algebra classes Monday and Wednesday, joint linear algebra classes where we're discussing eigenvalues right now. Right now, I'm giving a little bit of a lesson in real analysis. We've been looking at functional limits, and right now we're just proving some of the algebraic properties of functional limits from a real analysis perspective. So a lot of people have seen this from a calculus perspective, but now we're kind of backfilling in a little bit of the epsilon-delta theory about how this works. So we're just kind of in the process of proving these four particular properties. The first one is that any real number times f of x should land at k times the limit of f of x as x approaches c. So I just divide this up into two cases. The case where k is equal to 0 is dealt a little bit differently from the case where k is not equal to 0. When k is not equal to 0, then we can go ahead with our typical epsilon-delta proof. We'll just take epsilon bigger than 0, and then we're going to... how do we take delta here? Let's take delta to be, I think it's epsilon over the absolute value of k is what we want. Nice, Vin, nice. I feel like if we could collect your thoughts into one package, that would be nice. I feel there's a lot of tech happening in the chat on Discord. Okay, so let's take our delta to be epsilon over absolute value k. Let's go ahead and assume that our x minus c is less than delta. And if that's the case, then our x minus c should be less than epsilon over absolute value k. We can go ahead and do the multiplication. And then we can bring that through the absolute values. So oh, right, I'm an idiot. This is the fun part about teaching. We do have an assumption that we can use, right? We do know some information about f of x, and that's what I was failing to use here. So we know that this limit exists. So I'm going to need to draw on that here too, I think. And I need to draw on that first. Because what are we actually trying to prove? We're actually trying to show that k f of x minus its limit, we're actually trying to show this. And it's actually dependent on f of x minus L. F of x minus L, we know that we can bound that. So let me just jot down my thoughts here. So since... Maybe I should have done the construction phase. Maybe I would have saved myself a little bit of grief. So this limit exists. So since this is true, there exists a positive delta such that oh, Reese is out for a walk right now, guys. Sorry, you're getting an empty couch. If you, oh, also my dog cam's not working. Sad.
Fine, I'll integrate.
Where is Reese? Yeah, Reese is out on a walk. Yep. He'll be back soon, though. But it also looks like my camera might have got booted out by OBS, unfortunately, during the great reset of last night. Okay, so let's talk about this. If f of x has this limit as we approach c, and its limit is L, then I should be able to kind of bound this value by whatever I want. So specifically, I'm going to pick epsilon over absolute value of k. That's going to be my upper bound for the distance between f of x minus L. And once I have that, then I can go ahead and multiply both sides by the absolute value of k and distribute that k through to get k f of x minus kl. Less than epsilon, and that's what we need. So there's your secondary case. Okay, let's go through the construction for number 2. So for number 2, we want to show that the sum of these things is L plus M. So let's take a look at our rough work. We want to show that f of x plus g of x minus its limit is less than some number. Now, just for the sake of argument, let's pull this out for a hot second, and let's do a little bit of rearranging. So let's put f of x with its limit L, and let's put g of x with its limit M. And then I'm going to do this. And maybe somebody in the audience will be able to tell me what I've done here. So how do I know that this absolute value must be less than or equal to the sum of these two absolute values? Is Reese healthy? Yes, Reese is healthy and wealthy and fine. Hi, Fem. How are you doing? Welcome on in. Simple button down. Yeah, triangle inequality. Exactly. Both of you said that at roughly the same time, so I will award both of you your
Hardly even
QED
a
points.
practice test. QED.
Yeah, so this is follows directly from the triangle inequality. So what we want to be able to do now is we want to be able to kind of give an upper bound for this. We would like this to be bounded above by epsilon, and that kind of implies that each of these should be half of an epsilon. So if I could... Oh, I mean, that's the easiest way to do it. I can really bound this however I want. If I really wanted to, I could do like, let's bound this first one by epsilon over 4, and we'll bound the second one by 3 epsilon over 4. It doesn't really matter, right? We know that these two limits exist, so I can bound these by whatever value I want. It just happens that epsilon over 2 is the easiest one to pick, right? So that's kind of the common argument. If we kind of do that, then we should be all Gucci. So here's your proof. Take a positive epsilon, since this limit exists, and that limit exists, we have two deltas. I'm going to call them delta 1 and delta 2. So whenever x minus c is bounded above by delta 1, this is going to imply that the f of x minus L is bounded above by epsilon over 2. And similarly, I should be able to bound g of x minus m in the same way using delta 2. There we go. So we use the existence of those two limits to get the epsilon over 2's that we want. How do I choose the overall delta? Do you remember the trick from before? So the trick is, one of these deltas is probably going to be smaller than the other one. As long as I take the smaller of the two deltas, we should be okay. So let's take the smaller of the two deltas. That's going to guarantee that we get the bounds that we need for the f of x minus L and the g of x minus m. Then, if we assume that x minus c is bounded above by this particular delta, we have the following. We know that f of x plus g of x minus L minus m, remember we rearranged this to kind of group these things together in a particular way, and then we use the triangle inequality to break them apart. And then now I can lose the equality because I know that now each of these respectively are bounded above by epsilon over 2. And I get exactly what I want. I get that this particular function, f of x plus g of x, minus what we suspect its limit to be is bounded above by epsilon. Kind of cool, right? Symbol button down says, oh, points, thank you, very cool. I've only ever been on late enough to see non-math here. Oh, that's true, I know. I recognize the name. Yeah, I know you're usually in Dexy streams, and Dexy and I usually run Zelda and things like that. So welcome on in, where we usually talk about mathematics. Mathematics by day, Legend of Zelda by night. All right, 3 is kind of a fun one. I like this one a lot. We're going to do something a little unorthodox here. We're going to actually do a multiplication. Let's go ahead and multiply f of x minus L times g of x minus m. If we go ahead and do this multiplication, we get f of x times g of x minus, what do we get? Like L times g minus m times f, and then we should get a addition of L times m. And I'm going to go ahead and rearrange this a little bit. So I want to isolate this particular term. That means I'm going to have the multiplication. So we'll have f of x minus L, g of x minus m. And then let's go ahead and add the LG, MF, and subtract LM. And what we're going to do is we're going to go ahead and just take the limit as x approaches c of both sides. Now, some of these limits are relatively straightforward, like this is just a number, so this limit should just be L times M. Now, these two here, we've already done some work with these ones. So this is just a number times like a function that we know has a limit. So this is just by property 1. We know that this one should go to L times M, and this one should go to M times L. So we are going to get a subtraction of one of these things, but we basically get the following looking thing. We get the limit as x approaches c of f of x g of x. This should be equivalent to the limit as x approaches c of this multiplication. And then what are we going to pick up? I think we're going to pick up an extra copy of LM, right? One of them will cancel to 0, and then we'll get a plus L times M. Now, this is interesting because I believe that the limit of this should actually be this. This is what we want, right? And that's going to imply that this limit should be 0. So if I could show that that limit underlined in red was 0, then I would be happy with this particular proof. Simple says, it's neat to see epsilon-delta proofs in a real analysis context because I chose the applied track of math when you reach the fork. Yeah. So you went into a numerical. Very cool, yeah. I tried to do like a little mix of both. Like I did a little mix of kind of pure math. I really like linear algebra, so I tended to go down the linear algebra path. But my undergrad was definitely very heavy in applied mathematics as well. We did a lot of differential equations, a lot of Fourier series analysis and things like that. So I did a very similar thing. It was hard for me to, and I had to take like 3 statistics courses too. So my time was filled with a lot of courses that I didn't really care for. But that's okay, you know. that was a long time ago, so we're good. I have no remorse. Now, the cool thing about this limit underlined in red is we have f of x minus L. I know that I can bound that thing. And I have g of x minus m. I know that I can bound that thing. And I'm multiplying these two things together, so it kind of suggests that I should bound it by root epsilon. So that's exactly what I'm going to do. I'm going to take a delta 1 and delta 2 so that 1, when I bound x minus c by delta 1, this is going to imply that f of x minus L is bounded above by root epsilon. And we do the same thing for g of x minus m. Okay, so this is, again, we have to be given an epsilon, but given an epsilon, I should reasonably be able to find 2 deltas where this works. And so using our kind of classic real analysis trick, taking delta to be the minimum value of these 2 deltas that we know exist. We see that f of x minus L times g of x minus m minus its limit, well, we can just rewrite this as f of x minus L absolutes times g of x minus m absolutes, and we've bounded both of those above by root epsilon, so this must also be bounded by epsilon. So that shows us that this limit does indeed tend towards 0. And maybe I'll just write here, provided we know that that's true. There we go. So the limit, actually, let's just summarize it at the bottom. So I can come back up here. I can kind of grab some of this information. I know this limit tends towards 0. So the multiplication should be L times M. Very cool. So that's kind of a very classic way to deal with that particular problem. Yeah, I know, it's true, right? The Undertale Deltarune remix? Yeah, that's great. Someone also mentioned it's very fitting for a real analysis class because we're doing, like, mathemagics. Okay, so that should deal with the multiplication property. The last one that I want to show you, and at least give like a little bit of insight in how they set this up, is the division property. And that's pretty much going to finish most of our discussion on around limits. I do have a couple kind of questions. We have time. But let's at least finish up kind of the construction here for the last one. The last one's a little tricky. So the idea with number 4, right? So number 4 is that this f of x over g of x tends towards L over m. So the idea is, well, we just proved the multiplication property thing. So what we want to do is actually think about it like this. So let's think about it as f times another function. We're going to call that secondary function 1 over g. And then we're going to use 3 to get that the multiplication should be L times 1 over m. So the only thing we might have to convince ourselves is that the limit of 1 over g actually tends towards 1 over m. How do you check your QED? I believe it's QED counts. You have 1 QED point, famished. Okay, well, if that's the case, let's take a look at what 1 over g of x, like minus 1 over, let's take a look at what this looks like, right? Can I rearrange this? Can I try to get some insight in how we would be able to bound this by above by epsilon? Well, if we go ahead and find a common denominator, we'll get something like mg minus g mg. Which is kind of nice because the numerator turns into something that I do know how to bound. So when I go to find the common denominator, I do get some information. I can write this new expression that we have as 1 over absolute m times 1 over absolute g times, for the sake of argument, I'm just going to call it g of x minus m. Right? Whether or not I do m minus g or g minus m, it's the same thing, right? So that's good. I know how to bound this. So that's a good thing. 1 over absolute m, that's just a constant, so that's fine. So the tricky part's going to be dealing with this 1 over g of x. So the question now becomes, how do I deal with the absolute value of g? If I can somehow bound the absolute value of g, maybe I can figure out how to bound 1 over the absolute value of g. This is a tricky one, Zach. This is always a really hard one to kind of motivate and to explain. So if you have any extra insight as I'm going along, feel free to add it into the chat. So let's do a sneaky thing. Here's the sneaky thing. And I'm even going to call it a sneaky thing. I'm just going to take the absolute value of m, and I'm just going to rewrite it as m minus g evaluated at x plus g evaluated at x. So I haven't really changed the quantity here. I've just added 0 to this quantity. And then something kind of nice happens. I notice that I have that thing that I know how to bound, right? Remember, I know how to bound this. And if I apply the triangle inequality to this, again, for sake of argument, let's just say we get g of x minus m. So we get this. And that's a good thing, hopefully, because again, we know how to bound this, and this is the thing that we want to bound. So maybe I could input something for this g of x minus m, right? I can kind of upper bound it by something. That's going to give me a strict inequality in terms of capital M and maybe this absolute value of g, and then we can maybe figure out how that ties back to the original problem that we had. So I'm going to say, because there's an absolute value m on the left-hand side, what we probably should do is bound this in terms of absolute value m, just to make things a little bit tidier for us. And kind of the standard approach here is to bound this particular expression that I think they usually use absolute m over 2. And so the idea is we should be able to construct something that looks like this. We should be able to upper bound this g of x minus m by absolute m over 2. And again, remember, like, we know that this limit exists, so I theoretically can bound it by whatever I want. We're just choosing a nice fraction to work with here, right? I want to kind of group some of these terms together so that it's a little bit easier for me to talk about the absolute value of g and what it looks like. So go ahead and subtracting these things, we would get absolute m over 2 must be less than our absolute g. And we can take the reciprocal to get that 2 over absolute m must be bigger than 1 over the absolute value of g. So just kind of rewriting the order, now that shows us that this 1 over absolute g, we could theoretically upper bound it by 2 over absolute m, and then we can kind of come back up here and use that to our advantage. So I'm just going to kind of, in red, kind of finish off my thinking. We have 1 over absolute m times 2 over absolute m. How do I want to bound this? Well, I need all of this to end up looking like epsilon. So the classic approach is we need to divide out the 2, we need to divide out the m, and then we need to get an epsilon in here as well. So that's exactly how we're going to bound this first g of x minus m, and that should hopefully clean this up for us. Yeah, hooray for the power of flexibility, exactly. AKA choose any convenient small delta for the problem at hand. Yes, any convenient. In our case, we're choosing convenient small epsilons, which is always helpful. Okay, so hopefully that gives you at least a little bit of, I guess, insight into how we want to make this work. So to me, that's the playing around phase. So let's go ahead and actually prove this. All right, so we'll take our two limits. F is going to approach L, G is going to approach M. We're going to make sure that M is not 0 so we don't end up with some funky divisions because we need to have absolute M in the denominator of some stuff, right? So we're just going to make sure that M doesn't get unbounded on us, or this 1 over G doesn't get unbounded, basically. Let's go ahead and pick a positive epsilon as well. So since these limits exist, And I'm going to again just kind of use a couple of different deltas here so that you can kind of see how these deltas interact to give us our overall delta. So we have two deltas, 1 and 2. The first delta is going to be the first bound on G that we need, which was the absolute m over 2. Okay, so that was this one right here, right? So we just picked a convenient value here for this particular bound so that we were able to kind of get at the 1 over g of x bound. Okay, so that's our first delta. The second one that we need is going to be kind of our more overall one. We also saw that if we picked that as our convenient value the first time, then what we needed overall, I believe it was m squared epsilon over 2, if I remember correctly. Right, so when we kind of came back here and looked overall at, how do I turn this expression into an epsilon, I also needed to get a bound on this particular g of x minus m, and it looked like this. So that's our two different delta values. And of course, if we pick the smallest one of these, then we know that both of these are going to be true, and we can kind of use them interchangeably. So let's take the min of these two. And we're going to go ahead and consider 1 over g of x minus 1 over m. Now we've already done a fair amount of work above. I'm just going to skip to kind of the punchline here. We know that this converts into something like this. Actually, I'll go ahead and just write this part into the proof. And we're going to go ahead and note that absolute m, we can rewrite it like this. Apply the triangle inequality. And then bound this particular g of x minus m by, what do we need here? Absolute m over 2. And this leads to an upper bound for the absolute value of g. Okay, so just kind of go ahead and rearrange that, solve for g, take the reciprocal, and that's going to get this upper bound. So taking this back, we can now put that in up here, and that's going to give us a strict inequality between these two particular expressions. Now, of course, we can also replace this particular expression here with that other expression that we know is going to be helpful. That's going to be our m squared epsilon over 2, and that's going to give us our epsilon as desired. So there's our proof that 1 over g tends towards 1 over m. But we wouldn't be done with the actual proof. Now we just need to go back, use property 3 to finish everything up. So by property 3, we'll go ahead and rewrite this quotient as f of x times 1 over g. And property 3 guarantees that this is going to tend towards L over 1 over m, or just L over m. And there you go. Holy moly. We've proven a bunch of algebraic properties of the limit. Congratulations, everyone. You survived functional limits. So, that pretty much brings us to the length of time. Oh, you're welcome, Vin. Have a good sleep, man. That brings us to the end of our session here over on the Mandelbrot Mathematics server. So thanks all of you for joining and tuning in over in Mandel Maths. I'm going to go ahead, stop stream there. I'm going to continue and talk a little bit about continuity just for a little bit over on Twitch. So if you need to pop on over to Twitch, it's just my username. So I'll post a link here. HTTPS. I don't know if it'll let me, but I don't know if I gave myself the permissions. Twitch.tv/. So if you're not over there already, you can bounce on over into Twitch, and we will finish the discussion over there. So thanks again, everyone, over on Mandel Maths. Have a fantastic rest of your day, and hopefully we'll see you next week. I believe Horsey hopefully is putting together a presentation for us with regards to the derivative. And like I said before, if you would like to have access to some of those channels, just feel free to shoot me a DM if you don't have access to the real analysis channels already. And all of the notes that we took today will be posted in those channels. All right, so take care, guys. Go ahead and stop stream. And we'll go ahead and finish off the stage. Yeah, that'll hopefully save some resources for us over here in the Twitch universe. Okay, I don't think I have quite enough time for that, so let's skip that for now. And then, so what I want to do for the next, little while, I don't think it'll take me quite as long as the functional limit stuff, but I do want to touch a little bit on continuity as well. And what we're going to see is like a lot of our building blocks that we just took a couple hours to prove. A lot of those building blocks get ported over super nicely when we're thinking about continuity. So here's the textbook definition of continuity. It says a function, the domain here is A, so A is usually a subset of the real numbers, but we have like f acting on these elements in A, gets moved over into the real numbers, and we're going to say it's continuous at C. Notice here now that C is in A, C is in the domain. If for all epsilon, we can find this delta satisfying the implication. The implication now doesn't have that lower inequality of 0 because C is now inside the domain, so we have a little bit more flexibility with our, I guess, our lower bound in this particular case. But still, we can kind of upper bound this distance by delta. If we can do that, that's going to imply, when we bound the distance from x to c by delta, that has to imply that the distance from f of x to f of c can be bounded by epsilon. So it's going to look a little different, right? We're kind of missing that lower bound. We're missing that lower bound of 0 because we now allow c to be inside the domain. And then the other thing that changes is we don't have an L anymore. We have a f evaluated at c. So it might be worthwhile here just to kind of notice the two subtle differences. So the lower bound of like 0 less than, that kind of lower bound of 0 has been lost. That's just because this limit point is now inside of the domain. So we kind of assume that C is inside of the domain in these particular cases. Otherwise, it doesn't really make sense to talk about f evaluated at C. And so, like I said, that other little subtle difference is instead of capital L here, we have f evaluated at C. And this should hopefully feel very similar to the limit definition, with maybe a little bit of subtle hand waving. And Zach, if you're still around and have an answer to this particular question, I would be curious to get your insight, or anyone else that knows a little bit more of like the topological argument. It might just be me forgetting a particular definition or something here. But the textbook specifically makes reference to isolated points, I think, in saying that isolated points... So the textbook says that, this is what's usually given in calculus, and I do agree that that's true, right? We usually say that a function is continuous in a calculus perspective if this equation holds true. Now, specifically, Abbott says that this may not be true for isolated points, and I think it's because we can't create a sequence, and I could be incorrect there. Yeah, but the textbook definitely says this may not work for isolated points. So I would be curious to know other people's thoughts. So I was thinking to myself, that this definition may not make sense because we may not be able to construct. We may not be able to construct a sequence, right, for a specific isolated point in A. But the author definitely says this definition should work for isolated points because all we're doing is like looking at the points and kind of looking at these open neighborhoods around C and an open neighborhood around f evaluated at C, right? The function should work provided C is in A, and for isolated points, this definition should work. So I think the takeaway is you just have to be a little bit careful about thinking about continuity from a limit perspective, because you could run into some extenuating circumstances, I guess. So anyway, that's kind of my 2 cents about what the author's trying to say there. I could be interpreting that incorrectly. And I'm happy to open up a discussion there if someone wants to chat about that a bit more. So just to kind of get a feel for how the definition works, let's take a look at a crazy function, which is x. Sine 1 over x, that's going to be true when x is not 0. And we're going to define this function to be 0 when x is equal to 0. The question is g of x continuous at 0? So yeah, that's, again, maybe, let's see, simple. So for isolated points, is an isolated point, I get the impression that it's just a singular... Just a singular point that's just like living in by its lonesome. So alpha is an isolated point of a set if there exists an open interval of R whose midpoint is alpha, right? So it's an open neighborhood around alpha, which contains no points of S except for itself. So it's literally just a dot in the middle of the number line. Okay, so an isolated point is literally just like a dot. Like this. And for any, is it for any epsilon? I think it's just there exists an epsilon. Yeah, so there is an epsilon. So I can find an epsilon. Such that any of the other points, right? So maybe like this is also part of A. Right, so maybe A is that interval plus this isolated point C. I can find an epsilon that like strictly contains C only. So again, I think that's probably the problem. I think the problem is like if I try to construct a limit, I don't think I can necessarily get to C, right? If C is an isolated point, I can't really construct a limit that tends towards C. Right, unless I choose exactly C every single time. Right, so isolated points, I think, are a problem for this, the way that we would normally define a limit in the calculus. But, I mean, honestly, for the sake of calculus, usually you're dealing with relatively nice functions there anyway. But yeah, maybe I'll start bugging my professors that say this is the definition of continuity. I'll say, well, what if the domain is this plus a single point? How do I define the limit? I think of isolated points as arising from fk being defined only where k is an integer. Oh yeah, that could be like a function that's only defined over the integers. Is that what you're thinking? Yeah, rather than f being defined over the real numbers, f, the only input values we're allowed to use are integers. Yeah, I think things like that happen often in computer science, right? Where we're working with these very discrete kinds of structures, where calculus typically tends to be more about continuous kinds of structures. Anyway, I think it's interesting, and hopefully that gives a little bit of insight as to why the authors has some concerns. But what I want to actually look at this function, because this function, I want to see if it's going to break Desmos. So what is it? It's x sine 1 over x. Sometimes these things can get a little funky. So check this out. This is kind of cool. So here's x times sine of 1 over x. Oh, you're welcome. You're welcome. Like, if you want to come and chat math, we're here for you. This is like Mathematics Anonymous, like if you're really struggling with your daily dose of mathematics, you can come and, you can come and talk about it here. That's how we roll. So a very interesting function. It looks like, as we zoom in, it definitely looks like maybe things should be okay. It looks like a little bow tie. Right, Desmos is starting to break a little bit. We've entered the twilight zone. but it feels like maybe that limit should be 0. It feels like maybe we'll be okay. Let's see. This is a epsilon-delta proof, right? If I want to prove using the definition of continuity, I need to start with this thing and see if I can find the x minus c and figure out how to choose delta. So it's the same kind of pattern here. Let's do our g of x minus g of 0, and let's see what that looks like. So g of x is x sine 1 over x. G evaluated at 0 is 0. So we get something that we can actually break up as a multiplication. And that's kind of nice. So we know like this can never be bigger than 1. Right? Any sine and cosine function, that should be true, right? So if I maybe hide this one and I just take a look at sine of 1 over x, right? The largest that this could be is 1, the smallest this could be is -1. So I always have an upper bound of 1 for these kinds of functions, so that's nice. So I guess the other thing to notice is this is our x minus c as well. So what would we need? We would really just need this to be less than epsilon and everything should be fine, I think. So let's see if that's the case. Let's take a look at an actual proof. I think that should be okay. Okay, so let's take a positive epsilon. Let's take a delta equal to epsilon. And let's assume that we have x minus 0 is less than delta. So what does that give us? So that would give us that absolute x is less than epsilon. But we know that sine of 1 over x is always bounded above by 1. So we could probably sneak that in here like this. Right? Absolute x is really just absolute x times 1. So now we kind of have our upper bound. Actually, maybe I'll write it like this, just to keep the order okay. And then we can just put all this together. So we get x sine of 1 over x minus 0 should be less than epsilon. We can cut out the middleman in this particular case, and we will get that g of x minus g of 0 is always bounded above by epsilon. So g is continuous at 0. You liked my MA instead of AA? Yeah, true. Mathematics Anonymous. I should make a side channel on Twitch and just call it Mathematics Anonymous and just see if we can get people to join it just for funsies. Sometimes you just need to talk about math, right? And I mean, I'm not the only one that can talk math with you. There's lots of people in our community that'll talk math with you. For example, Zach is here. Zach and I host our linear algebra class Mondays and Wednesdays at 8 o'clock Pacific time. So that's coming up in a couple days. Oh my gosh, that's in 2 days from today. I've been working on some questions for Eigen things, which I'm super excited to chat about on Monday. And then, of course, we have others in our community as well. So we got Don, Stooky, Obi, and Dr. Gold. I think Dan's still on hiatus a little bit, but lots of lovely individuals that are happy to talk math with you if you need to. I can look forward to Monday. Oh my goodness. Nice LOL. Did it even work? Sometimes ChatGPT fails. Sometimes ChatGPT fails to send the message back to StreamerBot fast enough, and StreamerBot's just like blah 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 %. Like it gets entered as a variable, which is hilarious.
Zeta hilarious. But that wasn't a laugh. It was just me acknowledging your attempt at humor. Jokes are like math. Some hit, some miss. Got any Zeta clever ones to try again?
And so the reason why I kind of went in a bit of excruciating detail for a lot of the stuff with the functional limit stuff is because continuity really just feels like functional limits with that little addendum that the limit point can be inside the domain.
Geometry. Keep them coming, or let's tackle some serious math. Your choice. I'm ready to soar.
Polygon, oh my gosh. Terrible, terrible joke. Terrible. Hi, Dr. L. How are you doing? So we did a lot of work proving the sequential criterion for functional limits. That one just gets ported over relatively straightforwardly. So if we have limits tending towards C, and all of the xn's are inside of A, we know the limit point's inside of A, it should follow that f of x sub n should tend towards f of C in this particular case, rather than x sub n tending towards the limit L. And all of this should be kind of nice and defined, provided that this limit point is in A. So maybe we'll say C in A here just to be explicitly clear. That we would like that limit point to be inside of the domain. And of course we have a corollary that pops out of this idea as well. So with the sequential criterion for continuity, I wanted to show that the corollary that comes out of that sequential criterion, and we usually use this, in the other case we used it to show, I guess, divergence, or that like a limit didn't exist. So we can do this something similar here, right? With the sequential criterion, you can get this corollary out of it that basically can help you determine if continuity doesn't work. Simple. Thank you very much for the biddies.
Lunchtime, time for clear proofs, explanations, and fun discussion.
Much appreciated, my friend. Thank you so much. Doing well. Mexico is beautiful this time of year. What? You're in Mexico?
Bruh.
Invite me. Have a good lunch. Button down. We'll catch you later. What am I doing? I was confusing myself, and also there's some things that are broken. For some reason, streamer.bot isn't working.
Perfect calculations.
What?
Deliver perfect results.
Oh my gosh. Thank you very much for the Prime subscription, Dr. L. Enjoy your ad-free viewing, as well as access to all of your commands. So here's our divergence criterion, basically, right? So the sequential criterion for continuity says, if I have this limit point inside the domain, and I have a sequence that tends towards that limit point, then it should follow that f evaluated at that sequence should converge towards f of c, right? That's I think, a direct consequence of our sequential criterion for limits. The corollary then says, okay, well, what's the opposite of this? If I can find a sequence that converges to C such that f of that sequence doesn't converge to f of C, then I know that continuity can't happen, right? So that's a very nice corollary to have. It's a nice way to I guess, prove discontinuity for very awkwardly worded or awkwardly ruled functions. Just so you know, I have 30,525 pi points ready for Kakus. Oh gosh. I have good news for you. The good news is that the most recent beta release of Ocarina of Time, where we've been kind of playing the Anchor version, also has capability for crowd control. So all I need is a little bit of free time to play around with it. But yeah, we should be able to do a crowd control Ocarina of Time evening sometime soon. It's going to have to happen probably after linear algebra is done, or at least after real analysis kind of winds down here in the next couple weeks. But it's coming. Don't worry. And it has grass. It has pot sanity, grass sanity. It has crate sanity. It's crazy what this all has. It's quite wild. So let's take a look at an example just so you can kind of get a feel for how we use this divergence criterion. So I'm excited to battle my way out of copious flocks of cuckoos. All right, so the textbook uses this notation to talk about the greatest integer function, which I believe is also the same thing as the floor function. For those of you wondering, it's really just taking a real number and it's finding the largest positive integer. Well, is it n in n or is it n in z? Is it n in z? I guess if it's the greatest integer function, it should be n in z. But the idea is you're always kind of rounding, you're truncating, right? Rounding down, like truncating or rounding down is how I always think about it. And so it looks something like this. So if I input 0, the largest integer close to 0 would just be itself. So this is true for any, like if I put an integer in, it should just return an integer out. So I always get kind of like a step pattern of integers like this. But as soon as I go up a little bit, so as soon as x is slightly bigger than 0, then it's going to get truncated back down to 0, because 0 is the largest integer satisfying that property if I took like 0.1 or 0.2. So basically this is going to go all the way up to just before 1, and then right at 1 we get this immediate jump up to 1, 1. So we get almost like this staircase pattern that looks something like this. So this is what our greatest integer function would look like if we wanted to plot that. And so we're going to analyze, maybe what's happening at 1 or 2 or 3. We suspect that maybe at 1 or at 2 or at 3, there's a problem with the continuity here. So let's go to show. Discontinuity at 1, let's say. Let's go ahead and define a sequence. Let's call it x sub n, and I'm going to define it in the following way. I'm going to call it 1 minus 1 over n. And notice that as n gets really big, this should tend towards 1, right? It's going to be 1 minus some really small value as n gets large. So this should tend towards 1 as n gets big. Now, what about h? What happens to h of this particular sequence? Well, all of these numbers here are slightly smaller than 1. So provided I don't, jump too far to the left, provided we're looking at values that are, relatively close to 1. I don't take n to be some, I guess it's okay as long as n is a whole number. But all of these values, because they're slightly less than 1, hx sub n, all of these hx sub n's are 0. So this should just converge to 0. But we know that h evaluated at 1 is just 1. So there's a discrepancy between where this sequence converges to and the actual value of h. Right? So we've kind of shown that this corollary is true, right? We've constructed a sequence that converges to C, but this hxn doesn't converge to what we want it to, or what we expect it to be, which would be, we would expect that to converge towards 1. And I suspect with a little bit of crafting, you could probably craft sequences that work all the time for any integer value for this function. You could probably collectively show that all of the integer values are points of discontinuity for this particular function. Crate Z, oh my gosh. Is that definition equivalent to a left-handed limit? It's not equivalent. I don't think it would be equivalent to a left-handed limit, but you can think about it as approaching from the left-hand side, if that makes sense. So it certainly is going to feel like it's approaching. I think I understand what you're saying. Like, it feels like it's approaching from this direction, right? And I'm explicitly constructing my sequence to approach from that direction because I know that h evaluated at 1 is up here, but any sequence approaching from the left is going to have a limit value of 0. So yeah, I am kind of abusing my knowledge of what's happening over there, if that makes sense. So Hitch, welcome in, by the way. Why are sequences mostly used as the way to convert or to change a function to when dealing with limits? Is it because the most easy practical way to express, or is there a more fundamental reason? Yeah, I think Zach has a nice answer to that, right? So sequences do have the domain in the natural numbers, which makes it a little bit easier for us to kind of follow what's happening. So the natural numbers have that really nice property that we saw of countability, where the real numbers don't, right? The real numbers are not countable in some sense. So the natural numbers are countably infinite, and that does allow us a little bit of structure to play around with definitions, I think, right? Especially in a topological kind of sense. So yeah, I guess like lots of these kinds of applications can be boiled down to, let's just think about sequences approaching values and see what the outputs of those sequences are. And that feels like a very bird's eye view of what we're playing around with right now, and a lot of that framework is explored a little bit more in topology, I think. Right, like looking at functions, how functions map sequences here and there in open neighborhoods and things like that. Okay, I don't know if that answers your question. If you now have follow-up questions. So to finish off today, I have a couple algebraic properties I'd like to talk about. Just about the algebraic structure of continuous functions. And this shouldn't come as too big of a surprise since we're working with limits. We just kind of allow C to be a part of the domain. Most of the properties that we saw from earlier today are going to work. So I'm just going to jot them down here. We know that k times f of x. What do I need? I just basically need, let's just assume that these two things are continuous at C. Then a couple things are true. The first one is that k times f of x is continuous. And that's for any real k. So here k can be any real number. Second property is that f and g, when I add them, so the sum is going to be continuous. As you might guess, the product is going to be continuous. And then, of course, the quotient will be continuous provided it exists. Now, I'm not going to go ahead and prove any of these. A lot of the arguments that you're going to see for the proofs here are going to be very similar arguments to what we saw earlier. So I don't think it's beneficial to go back and rethink about these. They should feel, if you do research them, they should look very similar to what we did before. So I'm going to end off with one final theorem, and that's the composition of continuous functions is continuous. And we will actually prove that one, because this one it does have a bit of a different flavor compared to the others. So let's take f and g. Let's assume that f works from A to R and g works from B to R. And let's assume that wherever f maps A, that's going to be contained in set B so that G can act on F. So basically, I just want to make sure that the composition is going to be fine here. Okay, so we just want this to make sense. Okay, so this composition should act on A because the composition will kind of map those points through F first, and then G will act on those image points and send them into R. So this should be okay. So if f is continuous at C and if g is continuous at f of C, then we know our composition is continuous at C. All right, we should be able to go ahead and supply a quick little proof of this one. This one's not too hard. We're just going to use the sequential criterion here to get the job done. Get there even faster with Newton's method. Yeah, Newton's method is a numerical approximation, right? It helps. I think it helps find roots of functions, if I remember correctly, right? Oh yeah, Dr. L said that in the chat. Yeah, so basically you want to look at for square roots, yeah, x squared minus b is equal to 0. Yeah, exactly. Because it'll be easier to take derivatives of that, I think, right? All right, so let's work inside of set A. Let's grab a sequence inside of the domain such that this sequence converges to C. We know that f is continuous. So from our sequential definition of continuity, we know that this sequence fx sub n should converge to f evaluated at C. So next, let's just kind of look at this sequence that we get, the f of x sub n's. All of these should be landing inside of B because we know f evaluated at A. Kind of as a set, right? So f evaluated on this domain should land inside of B. Right? Its image is inside of B. Could be B, could be a subset of B, it doesn't particularly matter. But all of these values, fx sub n, these are all in B. So in other words, this is a sequence inside set B. And we know that this particular sequence converges to f of C, which is also inside of B. And we happen to know that G is continuous at f of C, so that's going to allow us to get the job done here. So since G is continuous at f evaluated at C, then we know that this should imply that G of this sequence should converge to G of that limit. Right, so now we're going to use the continuity of G. So what do we have? We have that if we start with a sequence that converges to C inside of A, this implies that g of this converges to g of this. And that's all we need. Right, so that shows that our composition is indeed continuous at C, right? And so all we're doing is we're using that sequential criterion from way back here, right? So we've picked one of these things, we've shown that this is true, therefore a function is a function is continuous. I forgot the word continuous. Okay, so continuity implies that every single sequence has this particular property, and that's what we showed down here, right? So picking a particular sequence in A and using the continuity of both F and G gives us the continuity of the composition. Kind of crazy, right? I don't know. It's been a bit of a fun day. It went a little bit longer than I thought it would, but you know, when you're doing some of those construction proofs, things get a little bit wonky. But I think that's going to be it for me for today. I just wanted to take some time again just to say thank you for all of you for tuning in. Thank you very much to Simple for the dono, and thank you very much for Dr. L for the resubscription. Much appreciated. We have some exciting news coming up in the next little while. I'm in the process of making the Elements nonprofit, which means that all of those donations, subscriptions that come in to help support this channel are going to start to get repurposed to rebuild the community, or to kind of build the community up a little bit more. So kind of be on the lookout for some of that happening here in the next couple months. Things are, of course, a little slow moving, but that's the life with legislative practices and things like that. So I'm just going to go ahead and start kind of winding down. What the heck? Let's put all of these back on. There it is. There. All of my overlays. Hitch, thank you very much for coming and hanging out. Yeah, you have a great day as well. It was a lot of fun chatting. I don't get the chance very often to talk about real analysis, so this was definitely a very insightful day. It kind of reminded me that I will probably never teach a real analysis class. And Dr. L, thanks again for the support. No worries. When are we back next? We'll be back tomorrow morning. So we're finishing up our joint presentations for the Friedberg linear algebra group with the Artin abstract algebra group. So Stuckey and I are going to be together at 10 tomorrow for the last linear algebra reading group session. And then Zach and I are back in the driver's seat Monday, Wednesday this week for the early morning linear algebra class. So be on the lookout for that happening this week as well. So hopefully we'll be back next week with another real analysis presentation on derivatives, and I'm hoping to get Obi in a couple weeks as well to discuss some of the really interesting theorems that come out from continuity, from derivatives, and that's basically going to kind of wrap up our introduction to real analysis reading group as well. So yeah, and then we'll get a chance to have a little bit of a break before we hopefully get fired up. I'm hoping to do some machine learning. That's what I'd like to do in the summertime. So kind of clean up some stuff that I need to with regards to the nonprofit stuff with StreamerBot, and then hopefully we'll start machine learning in the summer. So take care, everyone. Who is online? We have High Potential is on. Is anyone else online right now? Is Academy on? I'm gonna go do some snooping. It looks like just High Potential is on. Well, we can go say hi to Tinker. That's fine. What is that? It's what kind of prerequisite is needed for machine learning? So machine learning will probably have a significant amount of linear algebra and statistics attached to it, and maybe a little bit of calculus, depending on what we look at. I imagine that I'm going to have to review the statistics stuff. So we'll probably review the statistics stuff as we go. Linear algebra, I already feel pretty comfortable with, but we can review stuff as we go. And again, the calculus stuff I feel pretty comfortable with, but we can review stuff as we go. Because You're welcome, Zach. No worries. Yeah, so that's usually what I kind of think, is usually like a little bit of stats, a little bit of linear algebra, and a little bit of calculus go a long way for machine learning. But like I said, it's going to be a kind of a reading group style, so I'm happy to kind of review some of those things as needed as we go along. Because again, for me, like, I don't know how all of this stuff is connected to each other, and I kind of want to explore that a little bit more. All right, so thanks again, guys. We're going to sign off. We're going to go ahead and raid over into, let's say hi to Tinker. So if you need a raid message, they are there for you. Take care, everyone, and we'll see you tomorrow morning, same time, same place.